Before we start the talks, there's an announcement. If you need to get back to the hotel before the end of the banquet, there is a shuttle which will leave at 7 p.m. from the parking lot in front of the core building. Okay, so if you need to go, just let one of us know and we will get you. Otherwise, for those who are staying for the banquet, we try to arrange some sort of carpool so that people can go home safely. Okay, so the first talk in this afternoon session is by Rowland, and his title is Two Binomial Coefficient Theorem.
Right, so this is just going to be two sort of short stories in progress about number theoretic properties of binomial coefficients. So the first one is about counting entries modulo n. So the theorems of Kummer and Lucas are two theorems about binomial coefficients, sort of two classical theorems that have to do with something related to a prime p. Either we want to know the highest power of p that divides n choose n, or we want to know what n choose n is modulo p or something like that. And the main theme of this sort of this field in a lot of these theorems is what you do is you look at the base p representations of n and m, and that tells you a lot about what happens on p. Right. So what I'm going to be interested in particular is the number of binomial coefficients on the nth row that are congruent to a certain residue class modulo k. So let A, so kr of n, be the number of entries on row n of Pascal's triangle that are congruent to r modulo k. And so the basic question, the first question is, what's the structure of these sequences? What sort of classes do they belong to? What can we expect from them? So these are some pictures of, so this is Pascal's triangle modulo 2, modulo 4, modulo 8, etc. And generally we get these nice nested structures. So the coloring here is the zeros are colored white, and then the other residue classes are colored various shades of gray. And so again, basically what we're doing is looking at a certain row and counting the number of entries of a certain color on that row. Last bit of notation, let n sub w be the number of occurrences of this word w in the base p representation of n. And this comes out a lot of times in these things. The first such result was by Glacier in 1899, who showed that the number of odd entries on row n of Pascal's triangle is 2 to the number of 1s in the base p, or the base 2 representation. So you just write n in base 2, count up the number of 1 to c, raise 2 to that, and that's the number of odd entries on row n. For a while, then not much happened until the late 70s when Hexel and Sachs derived a general formula for a residue class of mod p. So here R is a primitive root modulo p, and they found a formula in terms of p minus 1 roots of unity for the number of entries on row n that are congruent to R to the I mod p. And from this they got these explicit formulas modulo 3, so this is the number of entries that are congruent to 1 mod 3, this is the number of 2 mod 3. You can see that they just depend on the number of 1s and 2s in the base 3 representation of n. They also got explicit formulas mod 5 in terms of these 4 things. Garfield and Wilf determined a way to compute this generating function. So this sort of wraps up all of these at the same time. So this is sort of a different take on the same problem. And then recently, I don't think this is even published yet, Zeilberger and Stanley sort of generalized the sort of arena of what people were looking at, and they showed that we have a multivariate polynomial with coefficients in some finite field, and raise this polynomial to the n power, and count the number of coefficients that are congruent to a certain invertible element in the finite field, then this sequence is a Q-regular sequence, meaning that it satisfies some linear occurrences of a certain type. And so this, of course, generalizes the binomial coefficients mod p case, because, of course, if we let f of x be x plus y, then raising x plus y to the n, we're getting binomial coefficients. Okay, so that's the situation with primes. What about prime powers? So mod 4 was the first prime power to be considered. In 1991, Davis and Webb gave these formulas for the number of residue classes, the number of entries congruent to 1, 2, and 3 mod 4 on the nth row of Pascal's triangle. And here, and here I should say that here NW still counts the occurrences of words in the binary representation of n. So we're not looking at the base 4 representation of n, we're looking at the binary representation of n still. And as you can see, these depend on the number of ones, also on the number of 1 So now we're getting dependence on subwords that aren't just of length 1. We also need to count the number of 1s and 10s. And what I want to point out is that if we just look at the odd residue classes, 1 and 3, then these 4 cases are either 0 or a power of 2. Okay. Not so remarkable, but is the fact that Glacier's result also shows that if we have an odd residue class, modulo 2, well, there's only one of them, then this result is also either 0, okay, it's never 0, it's always a power of 2. Right? So maybe there's a trend developing here. Is that at least for the odd residue classes, modulo some power of 2, when we count entries on the intro of Pascal's triangle, we seem to either get 0 or a power of 2. So then along came Andrew Granville, and this is a title of a paper he wrote in the early 90s, Zaphod Beetlebrock's Brain and the 59th row of Pascal's triangle. This title might make you want to read this paper. I don't know what would. This is really a delightful paper. I highly recommend it. I won't spoil the punchline about where Zaphod Beetlebrock's comes in. But in this paper, Granville showed that the same statement also holds modulo 8. So if we count the number of entries congruent to either 1, 3, 5, or 7, modulo 8 on any row of Pascal's triangle, it'll either be 0 or a power of 2. And he did this by basically computing the formulas for them. And they're not that nice. There's some case analysis to be done. But he pushed through it and got this theorem out of it. So this sort of begs the question, what about modulo 16? Right? We've seen this for 2, 4, and 8. What about mod 16? And maybe you can guess where this is going to come from now. The statement does not hold modulo 16. So it first fails at row 59. And Granville writes, unbelievably, there are exactly 6 entries of row 59 in each of the congruence classes 1, 11, 13, and 15 modulo 16. Our pattern has come to an end, but not before providing us with some interesting mathematics as well as a couple of pleasant surprises. And the other odd residue classes also fail if you keep going. So with all respect to Granville, I'm not so sure this is the end of the story, right? So the question is, okay, we don't always get zeros and powers of 2, but what do we get for odd residue classes? So up to row 2 to the 19th, which was not easy to compute, by the way, this is the set of values you get. For the first thing you notice is that this is the only odd number right there, and there's a reason for that, which is that the central binomial coefficients after row 1 are always even. So if you're counting odd residue classes on the nth row of Pascal's triangle, modulo power of 2, then it'll always be an even number. But not every even number appears. So 10 is the first even number that doesn't appear. And if you look at this, if you factor these numbers, then what you start to see is this sort of conjecture coming out. So these are the only primes that have appeared this far, by the way. So not very, the primes aren't very forthcoming. But you get this sort of picture that if this number is divisible by 5, then it also has to have a factor of 4 in it. If it's divisible by 7, then it also has a factor of 8, etc. So of course, there's no obvious sort of pattern. I can't predict. So 19 hasn't occurred yet. I expect that it will, but who knows? And what this power of 2 that will go with it, I'm not sure. So what one would like to do is sort of automate what Granville did modulo 8 for modulo 16, and sort of have the computers just do that all, and then hopefully we can just look at the formulas without having to do all the grunt work and sort of see where this is all coming. All right, so that's conjecture number 1. So conjecture number 2 is about the value of n choose m modulo n. Right, so why would we be interested in something like this? Well, once upon a time, you were reading calculus homework, and you got very mad when someone thought that exponentiation distributed over addition. But of course, this actually works sometimes. Right? So namely, modulo p, this is true because all these sort of inner binomial coefficients are divisible by p, which is not hard to show. Right? So how badly does the high school dream fail in general? Right? How mean should we really be when we're grading these calculuses? So in other words, what is n choose m modulo n? So here's a picture of the first few rows of Pascal's triangle, where on the nth row, I've reduced the entries modulo n, and then just on the nth row, colored each residue class 0 to n minus 1 from white to black in shades of gray. And so there's a lot of white, so those are zeros, so that's good. It doesn't fail horribly all the time. These rows where we just have 2 non-white cells sort of on the end are the prime rows. And one surprising thing I thought is that you can sort of see the Sierpinski triangle in here, even though we're not injecting 2's anywhere. We're just taking n for a mod n. We still sort of see remnants of Pascal's triangle mod 2 and things.